Hello all, welcome to another video from Basic Btech. So today we will discuss one important theorem from integral calculus, that is Green's theorem. So let's see what the theorem says and let's do one problem out of this. So let's start the video. So here is the theorem. It gives a relationship between the line integral of a two-dimensional vector field over a closed path in the plane and the double integral over that region it encloses. I will give you a graphical meaning. See, here is one xy coordinate system and I have marked a region here enclosed by the boundary A to B and B to A. Anyway, I have put the arrow starting from A to B, then B back to A, which means I have a counterclockwise enclosure of this region D. So, if such is the case, that is, this is a two-dimensional vector. Now, let's read the sentence again. It gives a relationship between the line integral of a 2D vector field. So, see, this curve is drawn in a 2D plane, isn't it? In an xy plane. There is no z quantity here. So, the curve is drawn in a 2D plane, the xy plane, and over a closed path in the region. And the region is closed, and so the line integral taken on that curve is equal to the double integral over the region. Double integral is taken for the region D, which is enclosed by the curve AB. Okay, so let's put this into equation. That is, if you have a function like integral, you are integrating this along this curve AB. Okay, let us mark it as C. So line integral C, okay, m dx plus n dy is equal to double integral taken for that region D. See, this is the region. Okay, double integral taken for this region D, and the integrand would be dou n by dou x minus dou m by dou y. Since it is a double integral sign, we have dx dy over here. Okay, so this is the basic expression for Green's theorem. It gives a relationship between the line integral of a 2D vector and it connects that line integral with the surface integral taken for that region which is enclosed by that 2D curve. Okay, so let's do one problem. See, this is a problem. Verify Green's theorem for the line integral C and the integrand is xy plus y square dx plus x square dy. This is of course in the form integral C m dx plus n dy, isn't it? Where C is a region bounded by y equal to x and y equal to x square. So let's start doing this by drawing an xy coordinate system. Also the curve is y equal to x and y equal to x square, which means this is a line and here is a parabola. So y equal to x means a line that passes through the origin, and since the coefficient of x is a positive number which is 1, we have a positive slope. Okay, so this is your y equal to x curve, and y equal to x square means it is a parabola that encloses your positive y axis. Okay, because y doesn't have any power. So here comes your parabola y equal to x square. Okay, so the region is definitely the region bounded by these two curves, which means this region. Okay, so let me mark this boundary. That is, first let us mark the corners. That is, the point over here is the origin 0, 0, and this point will be, let's solve this out, that is y equal to x square and y equal to x. So x square equal to x or x equal to 1, isn't it? So this has the x coordinate as 1, and then since y equal to x, we have the y coordinate also as 1. Okay, so this is your boundary points, and let us mark the direction in anti-clockwise manner. Okay, so this is your direction in the anti-clockwise manner. So there are two curves, isn't it? So let's mark it as C1 and C2. Okay, C1 starts from origin to this point and C2 starts from 1, 1 to 0, 0. Okay. So let's start doing the, actually this question is to verify Green's theorem. So what was Green's theorem? It says that integral m dx plus n dy taken for a curve is equal to double integral dou n by dou x minus dou m by dou y dx dy, isn't it? So we have to prove this, which means we have to find the value for LHS and value for RHS and have to see that both are equal, isn't it? So let us find out LHS first, which is the line integral. Okay, so let's do line integral first, and as you can see in the figure, you have got two curves, curve number 1 C1 and curve 2 is C2. Okay, so let us mark or let us do stage by stage, that is starting from curve 1. And what is this curve 1? It says it ranges from, or the x coordinate in that curve 1 ranges from 0 to 1, isn't it? So C1 has its x coordinate ranging from 0 to 1. Okay. So C1 is your curve who has got its x coordinate ranging from 0 to 1. Okay. So I have said how to do this line integral in my previous video, that is, if you have one integral sign or if you need to do only one integration, you have to convert all variables to only one single variable. That is, here in this case you can see x and y both are there inside this line integral. So we have to convert either y to x or x to y. Okay. So let's do, or let's convert y to x, because we have already written the x coordinate here, isn't it? So let's take everything or convert every y variable into x variable. Okay. So let's do it. Integral, actually this integral c can be splitted to two integral c1 and integral c2, isn't it? And firstly we are doing integral c1. Okay. So for integral c1, convert every y value into x value. So for this conversion we need one formula, isn't it? How to convert, or on what basis we can convert this y variable into x variable. So for that reference we need the curve C1 equation. What is the C1 equation? C1 is actually the curve associated with the parabola, or C1 is the parabola curve, isn't it? So y there is equal to y equal to x square. Okay, so we have to convert y variable, or we have to substitute y variable as x square. Okay, so integral C1 x into y here is x square plus y square is x square the whole square, bracket closed, dx plus x square. And what about this dy? Dy means, since we have got y equal to x square, dy means 2x dx. Just take the differential on both sides. Okay, so dy can be substituted with 2x dx. Okay, now let's reduce this. That is x into x square, x cube plus x raised to 4, and here goes your x square into 2x means it is 2x cube, and dx can be taken as common. Okay, now it is a normal integration and you can have the limits for x. What is that? X ranges from 0 to 1. Now it's time to do normal integration. It's x raised to 4 by 4 plus x raised to 5 by 5 plus 2x raised to 4 by 4 in the limits 0 to 1. Send it. So it is 1 by 4 plus 1 by 5 plus 2 by 4. This is the upper limit, and lower limit you have all the three zeros. So doing this you get, so that is 19 by 20. Okay. So line integration is done for the curve C1. Now next thing is to take the same line integration along the curve C2. Okay. There also we have the same steps, that is, for C2, what is the range? See, C2 starts from the point 1, 1 to the origin, isn't it? So the x coordinate ranges from 1 to 0, which is why I have marked the arrows, and the arrow marking is very important. also we have to mark it in anti-clockwise direction, then only we can accommodate this expression or this Green's theorem. If we mark in clockwise direction, we have to put a negative here. So, always follow one direction which is counterclockwise. So, here for the curve C2, you can see that the x coordinate starts from 1 or ranges from 1 to 0, isn't it? So, your x value ranges from 1 to 0, okay. There goes your x coordinate. Also the C2 curve, actually this curve C2, which is that curve y equal to x. So, in order to convert your y variables, you have to make use of this expression which is y equal to x, okay. There goes your reference values or reference points. Now, let us convert or let us do the integration. Let us see the question, integral C. For this conversion, you need to take y equal to x, isn't it? For that conversion, you need the expression y equal to x. So, every y value is taken as x, and obviously dy can be treated as dy will be equal to dx, okay. So, let us substitute everything here. X into x plus x square, that is x square plus x square is 2x square dx plus x square into dy. What's dy? Dy is dx. So, that is x square dx, okay. And this is now 2x square plus x square is 3x square dx, and there you have the limits or the x values ranges from 1 to 0, isn't it? So, it is normal integration now, 3x cube by 3, or it is simply x cube in the limits 1 to 0, and your upper limit is 0 minus lower limit is 1. So, 0 minus 1, you have the value negative 1, okay. So, your total integration, as we have done one equation or as we have done one integral equation, this thing, see, that is the whole of the curve integration is splitted into two. See, this is your curve. Integral C is taken as integral C1 plus integral C2, and you have got both of the values, that is integral C1 is 19 by 20 and integral C2 is negative 1. So, your value is negative 1 by 20. This is your LHS value, okay. This is your LHS value, and you have to prove that while doing your RHS also you will end up with this result negative 1 by 20. So, let us do RHS now. So, this is your graph and equation. Now, we have to check what about the value for RHS, okay. We have to find this value and we expect it to get as negative 1 by 20. So, let us see it. Okay, so for that we have to identify what is our m value and what is our n value. So, you can see that the function associated with dx is written as m and one along with dy is treated as n, okay. So, let us see the question once more. See, along with dx you have xy plus y square. So, this becomes your m and this becomes your n, okay. So, let us write xy plus y square for m and x square for n. Now, we have to move with the RHS, that is dou n by dou x means partial derivative for n with respect to x, that is 2x, minus dou m by dou y, partial derivative with respect to y is x plus 2y, isn't it? So, this into dx dy. So, you will have the value double integral 2x minus x is x minus 2y dx dy, okay. Now, for double integration I have done a video for this also, how to take the double integration. Firstly, you have to understand that for the outer limits, see, for this outer limit you have the variables, we have to take the outer limits for y, isn't it, and we know that here this is our region, isn't it. So, you can see that the y variable extends from 0, see the second letter, I mean the second number is the y coordinate. So, extends from 0 to 1. So, the y coordinate extends from 0 to 1. And what about the inner integral limits? That is, here the limits are the range of this x coordinate, isn't it. So, to take the limits for this x coordinate, we have to actually form or we have to draw a horizontal strip here. Okay, and for this horizontal strip, the left boundary becomes your lower limit and the right side boundary becomes your upper limit. And for this strip, you can see the left side boundary is y equal to x, isn't it? Or x equal to y. Since we have to take the range of x, range for x, we can write that x is equal to y here. Okay, the left side boundary, and the right side boundary is y equal to x square. Since we have to take in terms of x, or since we have to make equation for x, we can write it as x is equal to root y. Okay, so that becomes your upper limit, which is root y. Fine. So now let's do it. Let's do the inner integral first, that is this part. Okay, integral x minus 2y. Integral x is x square by 2 minus 2yx in the limit y to root y. Okay, so upper limit is root y the whole square is y by 2 minus 2y root y. Upper limit is ready, minus lower limit is y square by 2 minus 2y square. Okay, so simplifying you get, now again we have to integrate this thing with respect to y, isn't it? Also in the range 0 to 1. So integral c1, let's modify this itself, integral 0 to 1 dy. Okay, so that is y square by 2, again with this 2 it becomes 4, and minus 2 y raised to 3 by 2 plus 1 is 5 by 2 by 5 by 2 plus 3 by 2 into y cube by 3. Okay, let's put the limits 0 to 1. Here you can see the upper limit as 1 by 4 minus 4 by 5 plus 3 cut, it becomes 1 by 2, and lower limit is simply 3 zeros there. Solving you get what we expect. We have to get negative 1 by 20. Let's see. Yes, its value is negative 1 by 20, which is your RHS. Okay, hence Green's theorem is verified for this question. The question was, see a parabola and a straight line, the enclosed region satisfies the Green's theorem for this equation xy plus y square dx plus x square dy. Hope you like the video. If you like it, please do like, share and subscribe the channel. Till we meet in the next class, this is Minu signing off. Thank you and take care.